elementary idea of cross-field theory. When the stator winding is excited by the single-phase AC supply, then it produces an alternating flux phi s which acts along the axis of the stator winding. As rotor here is a closed one, the e.m.f. circulates current through the rotor's conductors and the direction of this rotor current is shown. Fleming's left-hand rule can be used to find the direction of the force experienced by the rotor conductors. When phi s acts in upward direction and increases positively, the conductors on left experience force from left to right and conductors on right experience force from right to left. In this way, the resultant rotor speed is 0. According to the cross-field theory, the stator flux can be resolved into two components which are mutually perpendicular fluxes, phi sx and phi sy. Two torques are developed, namely T1 due to phi sx and iry, T2 due to phi sy and irx. Under standstill condition, the resultant torque due to T1 and T2 is 0. Under some initial speed condition, the resultant torque due to T1 and T2 is not 0 and the motor will continue to run in the initial speed direction. At standstill, the stator flux lines are shown in y direction. In the first half cycle, the poles are N2A, S2B, and in the second half cycle, the poles are N2B, S2A, that is, they are reversed. For first half cycle, the rotor induces e.m.f. and current in the secondary transformer and thus a rotor flux in y direction is developed which opposes the stator flux N2S. So, no torque is developed. During running, the stator flux lines are shown in y direction. First half cycle the poles are N2A, S2B, and the second half cycle the poles are N2B, S2A, that is, they are reversed. For first half cycle, rotor induced e.m.f. and current as transformer secondary develops a rotor flux in xx direction as shown in the image. Since the rotor is running at synchronous speed, according to Faraday's laws of electromagnetic induction, rotor current cuts in stator flux and induces e.m.f. Rotor current or rotor flux lags the rotor e.m.f. by 90 degrees lagging. So, this rotor flux is called cross-field. The resultant two fields of stator and rotor form a rotating magnetic field that revolves the rotor at nearly synchronous speed. From the above discussion, it is concluded that at standstill, as there is no cross-field, the rotor cannot rotate. However, if the rotor is made to run by some external means, then it will continue to develop a torque as a single-phase induction motor in the direction of rotation.